All right. So
Okay.
where we left off on Friday was with this document that you were working with on your calculators, and we were finishing up with this last function here. Now, if I would go ahead and go backwards a little bit just to refresh our memory on this a little bit, we were talking about this idea of an area function, okay? And if we would write down maybe what this is, okay, if you want to maybe summarize, if we want to summarize here in our notes kind of what we came up with that last time and what I had started you off with, I think it would be this. All right, the concept we're talking about is an area function. Now, this is very much like the slope function, where we say we have an x as our input and area is our output. That makes a function. We need an input and we need an output. For every input, there can only be one output, right, to be a function. And this was the notation for that. Using our integral, it was a to x, where a is some fixed left endpoint, and the x, the right endpoint, is our actual input of our function. So this function, big A of x, this x inside the parentheses is the input to the area function, and that x is the right endpoint of our area. And it's the area under some function little f. And why do I have to use t's inside of here? Because we're already using x up here as the right endpoint of our area. We can't use x for two different things in the same problem. And so this x here, so the critical parts of this are the x that's inside of here is the same as this x that's the right endpoint up here. So we have to do two different things. Now, you're often given a problem where it says f of x equals, like for example, it might say f of x equals 3x plus 2. That's a problem we're going to do today. Little f of x equals 3x plus 2. Now, it's okay to have an x in there for little f, because remember, 3x plus 2 is the same graph as 3t plus 2, which is the same graph as 3w plus 2, which is the same graph as 3a plus 2. They're all the same, okay? So if I've got a little f function that's this, that's fine. I can have x in there, or any letter, doesn't matter. But when I put it in here, I can't use, and I want to use x here because the function I'm really talking about here is the area function. So I want x to be my input for the area function, so that x has to be there. So that means in here I got to use something else. So this little f would be 3t plus 2, right? If I could put little f of t here, or I could erase that. And I could put 3t plus 2 in there, be the same thing. That's little f of t, right? If I was told little f is this, then in here I would write it like that. So it always causes a little bit of confusion, but just understand that I'm using x to match this x here, okay? In here I can't use x again because that would be something different, all right? So this is called the area function. Now, what we're going to do here in a minute is we're going to graph this. So 3t plus 2, we're going to actually work this problem. 3t plus 2 would be something like this, right? And so we'd be talking about, you know, call this A, call this over here X, and we'd be talking about this area. Now, A is going to be a fixed left edge, but the X could slide back and forth. Those are supposed to be little arrows. The x could slide back and forth, okay? And every time I move to a new x, I get another area. I get an area for the output, okay? And that creates a function. So that's what we were talking about. All right, so we come back to this picture here. And so we did that. We said, okay, here's an area. Here's a function, 1.5, just a horizontal line. The area from 0 to 4 is 6. Then we go this way, 5, and we keep getting more area, right? And then they ask you to plot those areas. And so you did that. And what kind of picture did you have here? It was a diagonal linear equation, right? Because every time you move over 1 for your right edge, you were getting 1.5 more area. So every time you went over 1, you went up 1.5. Went over 1, 1.5. Okay, it was linear. And then they gave you a linear function, 1/2 t, right here. 1/2 x, 1/2 t, whatever. And now the area is also going up, right? But every time you move over 1, what happens? It's not exponentially. It's increasing. You're getting a new piece of area, an added piece of area, right? But what about that area that you're adding on? It's bigger, and let's use the technical term, chunks. We're getting bigger and bigger chunks of area. I was kidding about that being technical, more technical, okay? But we're getting, okay, because on the last one, what was happening? Every time we moved over 1, we got an equal piece of area each time. We added on 1.5 every time. But here, when we move over, like right here, when I move over 1, I add on a chunk of area. Right here, that was a chunk of area, kind of a trapezoid-shaped chunk. I move over 1 more, I get a bigger chunk of area. Bigger chunk of area. Well, what's the area graph going to look like then if I plot it? It was a parabola. Well, it was a curve. We kind of assumed it to be a parabola, right? And so what conclusion did you draw from that? I don't remember if anybody said it in here.
An area graph is 1 power higher than the antiderivative. Yeah.
1 power higher, which is antiderivative, right? Did we talk about that? I mean, but does it seem that that's what's happening? It seems to be that the area function is the antiderivative of what we're doing the area. Okay? Now that's kind of a big deal because it seems like, think back to slope. When we did slope, we did that whole f of x plus h minus f of x all over h, and we worked out those long ones, and x cubed came out to 3x squared, and x to the 4th came out to 4x cubed. It's like, wait, there's a pattern. The power drops by 1, and we do that whole thing. When you do the slope function, the power drops by 1. When we do the area function, it seems to go the reverse. Okay? Now, it's not a huge surprise. That happened to us the second day of class when we did the area under a velocity curve and we got position. And that was antiderivative. Of course, at the time, we didn't know that was antiderivative. But, okay? So there seems to be this kind of this connection between slope and area, this derivative, antiderivative thing. And then we took it one step further at the end of the day, that on Friday, and we did this one, and we started talking about this one. Okay, here's a parabola. Okay, so here we go. We're starting at 0. So 0 to 0, what's that area? 0, right? You obviously can't have any area. But then we come over here and we added a chunk of area, right? And then we added another chunk of area. So what's the area doing so far? Growing, right? The area was growing until right here. Now what happens? Now the area is going down. Why? Because we're adding on negative area. So now the area is going down. So now, listen to the words we're saying. We're talking about the area going up, increasing. We're talking about the area going down, decreasing. And then we said, where have you heard that before? That was derivative, okay? So let's do this. Let's start keeping track of this. So let's make our area function be here, our little f be here, and let's make, I don't know what to call it. Let's call it a chart. What the heck? We'll just call it a chart, for lack of a better term. Okay, so in the beginning there, my area was increasing, correct? So my area was increasing back here at the beginning. Now what did we notice about little f during that time? Positive. Yes. Little f seems to be positive. All right? Then once little f turned negative, we started picking up negative area. Right? And so that area is going down, down. Now the total area is negative and getting more negative, right? So the area is still going down, still going down, still going down till there. Right? Now what happens? The area is starting to go back up again because we're now picking up some positive area. Now right now it's negative and getting less negative, but pretty soon that area turns positive, the total area, and it's positive and getting more positive. So it seems like down here, the area was decreasing when little f was negative. Okay, interesting. So the area was decreasing when this was negative. Well, of course, we know that's the same connection. Where have we seen that before? Big F, little f, or F and F prime, right? So it's not a coincidence we called the area function capital A, right? Seems to be an antiderivative. That's what we were just saying a minute ago. Seems to be an antiderivative. Seems to have all these same connections we had with the chart and we have with slope. Now, if that's true, let's talk about concave up and concave down then. When the area function is concave up, what should be happening with the little f? Should be increasing. The concave down should be, let's see if that's true. Now, what's it mean for the area function to be concave up? If the area function is concave up, that would be one of these two situations. What kind of an area, what would the area be doing to have its graph be that? Getting what? Bigger chunks. Not exponential necessarily, right? I mean, because that means it have to be like e to the x or 2 to the x, but it's bigger and bigger chunks, right? That means the area is increasing, obviously, because it's going up. But it's not going up, but it's going up faster and faster. So that means we must be adding bigger and bigger chunks. Would that make sense? So we're not only adding area, but we're adding bigger and bigger chunks. Makes it go up faster. But concave up could also be going down at a decreasing rate. Well, what kind of chunks would that be? What would make an area graph go down if what's happening to the area? You're losing area, but not as fast. So smaller chunks. So you're losing area, but with smaller chunks, or you're gaining area with bigger chunks. Wouldn't that make concave up on your area graph? Okay, so let's go down and so concave up, though, we say should be happening when f is increasing. Okay, so let's go back to our picture, and let's see if that's really true. Now, where's f increasing? Well, little f starts increasing right down here. Everybody good with that? Right down here, little f starts increasing. Okay? Right? Because this is little f right here. Okay, so let's go back to that point. And let's see what's happening with the area. Okay, so right here. So what's happening with the area? Well, what happened right there? When I just took that step right there from 7 to 8, what kind of chunk did I just add there? A negative chunk, but getting smaller. Aren't the chunks getting smaller right now? The chunks of area are getting smaller. So what I'm doing is adding negative chunks, but smaller and smaller negative chunks. Well, what's the area graph going to be doing now? It's going to be going down because I'm adding negative chunks, but smaller negative chunks. So it should start leveling. Is that concave up? That's concave up. Okay? And then what happens? Well, getting smaller and smaller negative chunks until here. Now what am I at? Bigger and bigger positive chunks, which means the graph's now going up like that. Concave up. So it seems like when little f is increasing, the area graph would be concave up. Now let's look at the reverse of that. When little f is decreasing, which is back at the beginning, the area graph should be concave down. Well, what's concave down look like? Well, it could be that, or it could be that, right? What's that mean if the area graph's doing that? Negative chunks, but bigger negative chunks. So that area is going down faster. Or it could be positive chunks, but little, smaller positive chunks. Okay? So that would make concave down. Well, that should be when little f is decreasing. Now let's check. Back here when little f is decreasing, what are we adding here? Smaller positive chunks. So that graph would be going up, but leveling off because I'm adding smaller chunks. And then here, if I go this way, I'm adding negative chunks, but bigger and bigger negative chunks. So that graph would be going down and going down more steep if I was plotting those areas. So it seems to fit. The area function seems to be the antiderivative. It seems to fit all the graphical stuff we've learned before about the chart. Okay, it seems to fit. So that's pretty cool. How, slope, area, they seem like two totally different things, but yet now there seems to be this connection. All right, here's what we want to do today then. We want to extend that not from the graphical into the symbolic. How does that power go up one? How do we get a formula for the area? And here's what we're going to do. So we're going to actually do part of your homework. On your homework sheet, the the 5.2 line. Okay, 5.2, day 1, which would be just that the top line. Okay, 5.2 in bold, it says 21 through 28 we're going to do in class. Okay, we're going to do that right now. Now you can do it in your notes. You can do it in your notes if you want instead of on your homework page. That's fine. Okay, and they're just there because when you do 29 through 36 for your homework, it's going to pretty much mimic what we do in 21 through 28. Okay, just with a different little f. All right. All right. So here we go. So they start out by telling us little f of x is 3x plus 2. They tell us that big F of x, what's big F of x? This is on page 320. Big F of x is the integral from 0 to x. Now, little f of t, I don't want to write little f of t. I want to actually write little f in there. So what should I write? Oh, 3t plus 2, right? Can't use x for little f there because I'm already using x as the right edge and the input to my big F function. So I got to use something else in here. We usually use t. Okay, just something other than x has to be. Okay? So what that is saying is big F is the area function from 0 to some right edge x. And as x changes, the area will change, and that denotes that function. Okay, what's big G of x? They tell us big G of x in there. From 1 to x of the same little f, right? So it's the area under that same little f function, except now it's from 1 to x instead of from 0 to x. So that's different, right? That's going to be a different area. Right? So big G will be different than big F. Okay, and big H is what? The integral from -2 to x. So the only thing changing is our left edge. And so that's what we want to investigate today. So what we've been saying is that the area function seems to be an antiderivative. But how many antiderivatives does a function have? Why an infinite amount? The plus c, right? That plus c. So somehow this plus c's got to be involved here somehow, right? So that's the thing we're kind of investigating today. All right? So big F, big G, big H, okay, are these, they're all the area under this same little f function, but with different left endpoints. All right. So here's what we're going to go through. Now on this page, let's do big F. So we want to make a picture of little f here. A pretty decent picture if we can. It's going to go up to going to have a slope of 3, which means it's going to go down 3, left 1, it's going to go up 3, over 1. Something like that. Right? So that's the little f function for 3x plus 2. Now let's work with big F here first. So big F is going to be the area from 0 to x. Now where should I put x? Well, let's just put it over here somewhere. We'll put it between the 1 and the 2. Okay? We just have to have, but it could be anywhere, right? That's going to shift, slide back and forth. Remember I did some of that. Well, we did that with the red area, right? I was taking that right edge on the calculator document. I'm just sliding it back and forth and showing all the different areas. So what we have is we're going to have this area right here. But I put these little arrows on the x to just show that I can be grabbing that and sliding it back and forth. Matter of fact, we could even slide it over onto the other side of 0, which would be weird. Now our right endpoint's on the left. Oh yeah, we know how to handle that, right? When you're going backwards, what happens? Everything's opposite, right? Okay, but just to keep it simple, let's just keep the x over there on the right side. All right, so what kind of shape do we have? Trapezoid. Okay, so big F. Now remember, big F is supposed to be the area under this curve from 0 to x. So this picture should be the big F function. This area should be the big F function. So let's do it. So let's write that area. Be 1/2 the sum of the two bases. What's the left-hand base? What's this base? The base of my trapezoid, right? This right here is 2, all right? Plus, what's this one over here? What would this be? Well, how did we get 2 here? No, it wouldn't be 5. If we were right at 1, if you put in a 1 into the function, you get 5. We put a 0 into the function here, got 2. But where are we at here? What's our input here? Yeah, it's 3x plus 2 is what it is. Right? Because it's going to change, right? Remember, when we slide that right endpoint, that base there is going to change. That base depends on x. So how do we get it? Well, it's an input of x, so we go into our function and we plug in an x, right? 3x plus 2. Plug an x in for x or in for t, you get 3x plus 2. So this base is not going to change. That's fixed. That's 2. But this base over here is going to change. So that's x plugged into the function. That's 3x plus 2. All right, times the height of our trapezoid. And this is our height right down here, right? Because it's a trapezoid tipped up on its edge. So the height is this down here. What is that? That is x. Okay, so there we go. So that ought to be our function. So let's do this. Let's bring the 1/2 x around in front. And what would this be in here? 3x plus 4, right? If we simplify that, that's 3x plus 4. And then let's distribute that through. And we get what? 3/2 x squared plus 2x. Does anybody notice anything interesting about that? Yeah. Okay, let's take one thing at a time. First thing we're noticing is, now, it shouldn't surprise us since this came out to be the antiderivative, right? Because that's what we've been saying. I mean, that's what we just got in saying. We said the area function, according to the chart stuff, seems to be the antiderivative. So it shouldn't change. It should not surprise us at all that it came out to be the antiderivative. Now, I still think, it deserves a ooh or an ah. Okay, thank you. It deserves an ooh or an ah, because look what happened. I mean, it came from trapezoid. Just like our slope formula was our definition derivative, and we got these great, bring the power down in front, drop the power by 1 kind of things for slope. I mean, derivative, wow. And then this, the area of a trapezoid, we just drew the picture, and we got a trapezoid, and we just worked out the trapezoid, and it ended up being the antiderivative. I mean, that's kind of cool. But it doesn't surprise us because we saw it had all those connections. All right, now the question, you said something about the left edge.
So like if you did your g of x one, wouldn't you do the antiderivative would be 3/2 x squared plus 2x plus 1 for your g of x?
Let's see if he's on the right track. What he's saying, I think, let me paraphrase what you're saying. He's saying, couldn't we have just said, hey, we realize this is the antiderivative. So do the antiderivative, raise that up to 2, divide by 2, antiderivative as that. So that's 3x squared plus 2x. And then understand that there is a plus c in there. And you're saying since this was a 0, you just put a 0 in there, you get, but if you put a 0 in there, you get 2.
Well, no, I'm saying.
Oh, you're saying just whatever the left edge is your c. You add that onto the end. So the next one might be a plus 1. Okay, let's see if it comes out. Now, we are going to go ahead and do G and H the same way with pictures and work it out. On your homework, number 29, you're going to do the same thing. You're going to go through it. Now, I'm not going to make you do that on a quiz, and we're not going to have, it's kind of like the long way when we did those derivatives a long way, and we did them for a little while, and then we didn't really have to do them much anymore. Kind of the same thing here. And I won't even make you do this on the quiz, but I do want to work this through and see. Now, see, this would not have worked if our little f was a parabola. If our little f was a parabola, we wouldn't have been able to do this because we'd have had an area that didn't work with geometry. See, only because this made a geometric area does this work. But I think it's really neat to show, wow, there it is. I mean, antiderivative formula even comes out of here. Okay, so let's go to the next one. And let's see if Zach is right. So for the integral from 1 to x, now we don't have to be quite as fancy with our picture this time. This is a g of x, right? So our picture was essentially, let's see, it kind of crossed through here, kind of went up through here like so. Okay, so now at 1, so this is going to be at 1 right here, and then this one over here is going to be at x somewhere, and that's going to slide, right? That right edge can slide. So basically I've got this trapezoid. Okay? All right, so what is that formula? Well, it's a trapezoid, so it's 1/2. Now, what are my bases? Slow down. So the only difference between this one and the other one is the one went from 0 to x, and this one goes from 1 to x, right? So what's my left-hand base here, the one going up here on the left? That's 5, right? You just plug a 1 into the function, and you get 5, right? Plus, and then what's my right-hand one? 3x plus 2 again. Again, I take x and I plug it into the function. I plug it in for t, and that's 3x plus 2. Okay, and then what's my height of my trapezoid? Well, that's this right here. Isn't that x minus 1? Right? It's the right x-coordinate, which is x, minus the left x-coordinate, which is 1. X minus 1. Right? So that'd be x minus 1. Okay, now let's simplify this a little bit. That'd be 1/2. I'll just leave that setting out there. This would be 3x plus 7. And then this would be x minus 1. Oh, so I got a FOIL. All right, well, we can do that. What do I get when I FOIL this? 3x squared. No. 7 on the inner, minus 3 on the outer would be plus 4x, minus 7. And then finally, we go ahead and distribute through the 1/2. 3/2 x squared, oh, that looks familiar, plus 2x, that looks familiar, minus 7/2. Okay, so it didn't quite work out like Zach thought, but I think he's on to something. His main point was that the 1 and the 0 have something to do with the c. Have something to do with it, and I would agree with that. Yes?
I think you got to plug in the distance into the antiderivative and then solve for the c.
Somehow that's going to happen, and I think you're right. And I'm going to show you the particulars about that. But before we do that, I want you to think of it in a different way, instead of just plugging in. Now, let me say this again. What is the difference in the two pictures? And I wish I could have them both up here. But what is the difference, and you guys have them on your paper, what's the difference in this between this picture and this picture? Right, I mean, the endpoints, right? The 0 and the 1. But in terms of area, what piece of area is different in one versus the other? This piece of area right here, right? The g function does not contain that blue piece of area. The f function does. So on the f function, if x was 5, for example, right? If x is 5, the f function would go from 0 to 5. The g function would go from 1 to 5. What's the difference? The piece from 0 to 1. What's the difference between any two antiderivatives of a little f function? The plus c, right? A constant. What is that piece of area from 0 to 1? A constant, right? It's a fixed piece of area. So when you change the left edge, the only thing that changes between the area functions is the difference in their left edges. So if I did an integral that went from 2 to x and another one that went from 5 to x, what's the difference between those two? The piece of area from between 2 and 5, right? The only difference in a function that goes 2 to x and one that goes 5 to x is that fixed piece of area from 2 to 5. That's the c, or that's the difference in the c value. Okay, let's do one more. Let's do h, and let's see what happens on that. And then we'll come back and talk about what Ryan said which is where this, how we would get this negative 7/2. Because I told you, I'm going to make you go through this process on number 29. We're going to do it with h, and then you're going to go through this with a new little f, big F, big G, big H. Not by just doing an antiderivative. You're going to do it by doing areas. Okay, but after that, from now on, we'll be able to do it with just antiderivatives. And I'll show you how that'll work here in a second. All right, so here we go. So now we're going to do big H. And big H was the integral from -2 to x of 3t plus 2 dt. So again, let's draw our picture. Try to be a little more careful with this one because it does matter just a little bit. We're going to have to start over here at -2. 1, 2, 3. Okay, we're going to go up here, cross to down here somewhere. Okay, and it goes up like so. Okay, so now this time we want the area from -2. Now I'm still going to put the x out over here somewhere. Okay, so I'm going to put x right in there. So we're talking about, now what we have, instead of a trapezoid, we actually have two triangles. Now I could have put that x over here on the left. I could have put it in between. It's just easier, I think, if we just put it over here, off to the right, out here somewhere. So what I now have are two triangles. Now again, imagine that I was grabbing this x right edge and just sliding it back and forth and giving us new areas, just like we did back here. Just taking this right edge and sliding it around and getting an area and then getting a new area here and so forth. Okay, that's what you want to imagine happening here. All right, so what is my area? Well, it's the first triangle, which is a fixed triangle. As long as my x points over here, it's a fixed triangle, right? Now, I could move the x in there, but just it would work out the same. Just trust me on that. Let's just keep it simple. So what is this rectangle? Well, we need to know where that crosses, right? Because we need to know this base. How would we find where that crosses? Set this equal to 0. So 3t plus 2 equals 0. Right? So -2/3. So this is at -2/3 right here is where that crosses. So we need to know that. Okay, so what I have is a triangle here. Will that triangle be half? What's the base? What's the height? What's this base right here? 1 1/3, 4/3, right? Because we know this is 2/3, so that'd be a third to there and then 1 to there. So 1 1/3. And then what's this height right here? -4, right? We just take -2 and plug it into the line function, right? -2 times 3 is -6, plus 2 is -4. And it would be negative, right? That's a negative area down here. So I'll go ahead and put the negative in there because we know that's a negative area. It's below the x-axis. Okay, so we're going -2 to x. All right, now we got this triangle, so we got to add that on. Okay, so 1/2. What's the base of this triangle here? X minus -2/3. That'd be x plus 2/3. Well, that makes sense because x is measured from 0, right? X is measured from the origin, right? So this would be x, and then this is 2/3 right here, right? So x plus 2/3. So that makes sense. So the base there is x plus 2/3, or x minus a -2/3, same thing. And then what's the height? 3x plus 2, same thing. We plug x into the function, and we get 3x plus 2. Okay, so we got another FOIL situation. So what about this fraction here? What do I get when I multiply that out? -16/6 would be -8/3 plus, and then I'm going to have a half, and then I got to FOIL this. So let's FOIL this. What would we get? X times 3x, that's 3x squared. Inners, what's 2/3 times 3x? 2/3 times 3x, that'd be 2x. Outers would be 2x. Oh, look at that. What's familiar? 4x. Last times last, what's 2/3 times 2? 4/3. Okay, now let's distribute that half through there. would be 3/2 x squared plus 2x plus, what's half times 4/3? Half times 4/3? 2/3. Okay, now I can add my negative 8/3 plus my 2/3. There we go. 3/2 x squared plus 2x minus 6/3, which is minus 2. Okay. Oh, now that was interesting. So it worked on 2 of the 3, right? So this -2, if we played it, it ended up being -2. So why didn't it work on that one? Maybe we screwed something up. Zach's actually right. No. But that was a good thought. So obviously we got the antiderivative every time. The thing that changed was those where the left edge was. So it had to do with the area, right? It had to do with the difference in the areas, okay, between them, which had to be where the C came about. All right, so if we would look at the area from -2 to 0, so I think what would happen, Zach, if we took this area here and this piece right in here, if we took those two and added it together, that would add up to -2. And that's why that worked. And then on this one, if we would take this missing piece of area, it would be the 7/2, right? And it would be negative. Why would it be negative? Because the integral goes from 1 to x. Well, if we go back from 1 to 0, that would be negative area. So that's why that ended up being negative. So that's how you can figure if you had a picture and if you were doing area, which of course only works if it makes lines and makes something that we can do with geometry. And most functions won't do something with geometry. So we'll have to have another way. Well, it has to do with antiderivatives. And this is what Ryan was talking about. So let's go back to this one. And let's see how we could relate this to something we've known before. All right? So here's the big F graph, or the big F integrals from 0 to x, 3t plus 2 dt. Okay, so what Ryan was saying was we could, and kind of what Zach was saying to start it, is when we see this, and this is probably the number one thing you need to take away from today. The number one thing you need to take away from today is when you see this, it makes you think what? Antiderivative. That's the number one thing you take away from today. When you see this area function from some number to x, it means antiderivative of whatever little f is in here. Antiderivative. So your first step would be do the antiderivative. So if you were going to try to find what this big F of x was, you would start by doing the antiderivative. So we'd raise that up to a 2, divide by 2, except it would have x in it. We saw it ended up having x in it, not t. All right? It ends up, because x is the input, so it has x in it. Antiderivative of 2 is 2x, plus some c. Right? We don't know, but every antiderivative has a plus c. So how have we this year found that c? We need an initial value. It's an initial value problem. And in a sense, that's what this is. Little f is like a derivative. That's like your differential equation. We need some initial condition for big F. We need to know, there needs to be some big F that we know. Is there any big F value that we know in this problem? Big F of anything. Is there big F of something that we know? I'm telling you this. Yeah. What is big F of 0? Okay. Here's, some of you are saying 0, you're seeing it, but not most of you are not. Look right here. Look right here. This is something I want you to, you're going to need to be able to see this in your homework. This is big F of x. This x here is that x there, correct? So if I say big F of 0, that's saying put a 0 right in for that x, which means put a 0 in for that x, which means that's the area from 0 to 0. What is the area from 0 to 0?
0.
There's no area. That's 0. What I'm telling you is when you get an area function and know the left edge, you get an initial condition for free. Right? It was there. It was there the whole time. It's just not written the way we normally see it. But right there, you know, big F of 0, if you put a 0 right there, you know that is going to be 0. So let's look at that the way we've always done it. So we know in that area function, if we put a 0 there, means put a 0 there, that comes out to be 0. So now what do we do with this? What do we do with this big F and this? We put a 0 in here for x and set it equal to 0. C's got to be 0. Sure enough, that's what we have. C was 0. Okay, let's go to the next one. Okay? Now, forget this stuff down here for a minute. We would look at this and we'd say, hey, big G, when we see this area function, we think what? Antiderivative. So we would do this antiderivative, except we put x in there, not t. And we would get this, and we'd get some plus c. But what G initial condition do we get for free? G of 1 is 0. Because G of 1 means put a 1 right there, which means put a 1 right there. The integral from 1 to 1 is 0. So this is the initial condition that was there all the time in hiding. So now what do? We put a 1 in for x. Right? We put a 1 into our antiderivative for x, and we work it out. What's 3/2 plus 2? 3.5, which is 7/2, right? What do we get? Look at that. Can I get an ooh or an ah? It's kind of a fake one, but that's all right. It makes it good enough. Right? That's how we can get it. Now, when you do number 29 today, I don't want you can double check it that way if you want to, but I want you to draw the picture, do the area function this way, whatever. But what's happening there is we're getting an initial condition. When we're given an area function, we think antiderivative, and that left edge is like getting an initial condition. Okay? Now, so that's part of what we want to be able to do in this section is be able to find that antiderivative formula, okay, using the idea of antiderivatives. But we also want to have a bunch of, there's also going to be a bunch of questions that are about the chart. Most of the questions are about the chart. I hope you find it pretty easy. A lot of the questions on the quiz are going to be about the chart. Now, the only difference is we want to think of them in terms of areas, not so much slopes. As a matter of fact, on the homework, I'm going to encourage you to think of them both ways. Think of them as slopes and think of them as areas. Okay? And so let's take a look at what that would look like. So first I've got a thing to show you here. Okay, so let's take a look at this. All right, oops. Okay, so here's this same area function we just been working with, 3t plus 2, okay, from 0 to x. All right, and so we have our area and we're going this way. We can even go backwards, right, because this would be a negative area right back here. And this is negative, 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 and then we start picking up some positive area and so forth. Now, because we're backwards now. From a to x, this would be, this down here would be what kind of area? This area down here. This is positive because our integral's from a to x. Here's a. Here's x, that's backwards, so this is positive area, this little piece is negative, so overall my area is positive. Okay? All right, so we look at all those things. Now we want to connect it with this idea of the antiderivative. Okay, so what I've done here is I've plotted the area. That point is a plotting of the area. Okay, right now we have a positive area, so that's where it's up there. And as we go this way, we're getting more and more positive area, so that area thing goes up. Let's go way back over here like we were talking about. Right now we got a positive area, positive 22. This area down here is positive, right? So as I slide this, what's happening to the area? Because we're losing positive area, right? And we're losing smaller and smaller chunks of positive area. So we're losing smaller and smaller chunks of positive area, so this area is going down. Now right here we don't have any area, right? Because the positive and negatives canceling each other out. So the area is 0. And now we've got negative area. So the area is below the x-axis. So this dot's down here. But now we quit losing the positive area and we start what? We start losing negative area. Well, what's that mean if you lose negative area? You're actually gaining area now, right? So the area graph starts to go up. So that dot starts going up. We've still got negative area, but it's getting less negative. So we're losing negative area until here we have no area. Now we're gaining positive area. And we'll continue to gain positive area, bigger and bigger chunks, and so forth. So if I was to plot that graph, it would look like this. And so going back, right, negative area, but I'm losing negative area, so that, or excuse me, I'm losing positive area, so my area graph's going down. Right here I have no area. Now I've got negative area, getting more negative. Now I'm losing some positive area, or excuse me, yeah, I'm losing some negative area, excuse me, so the area's going up and up and up. And sure enough, we have a line, it looks like a parabola. Now, here's the really cool part. What happens if I change the left endpoint? What did we just get done saying in F, G, and H? When we change the left endpoint, what happens? You change the C. What should that do to the parabola then if I change the left endpoint? Shouldn't it just shift it up and down? Yeah. Right? If I change the right endpoint, all changing the right endpoint did was give me a different area, a different point on the area graph. But if I change the left endpoint, I get a new function. But it should just be a shift up and down. Now this would be really cool if this actually worked. Can't imagine it will, but let's try it anyway. So if I move the left edge, wait, ready? Same function, different C. It still gets me every time. All right, so if I seem a little choked up right now. All right. I don't even know what to do after that. All right. So the big thing for today. This is one piece of what's called the fundamental theorem of calculus. The connection between area and derivative. Okay. The fundamental theorem of. I mean, just the name is kind of a big. Sounds like it must be a big deal, right? The fundamental theorem of calculus. This connection between area and slope. All right. So we're going to have some. There's going to be some chart type of questions. There's going to be this area kind of question. So let's go through 21 through 28. So on page 320, okay, 21 through 28. Now what did we just do? All that work we did with all those pictures, those three pictures, was what? That was 21. Okay, all that was 21. So when you do 29, they give you new little f. You know, maybe you want to start with that one. But now 22 through 28 go really fast. So 22 says find the number such that. Find a number C such that G is equal to big F plus C. Well, that'd be 7 halves. Now, would it be 7 halves or negative 7 halves? You want big F plus C to equal G. Yeah, so what would you have to add? In other words, what they're saying is, what would you have to add to big F to make it equal G? Would it be negative 7 halves? It should be negative 7 halves, right? Because basically what that says is big F plus what would equal G? Well, they're exactly the same except for the constant, negative 7 halves. But you always have to think a little bit, is it positive or negative 7? Because if they would have had the plus C over there on the G side, then it would have been positive 7 halves, right? Okay, so you do have to be careful there. But all that sentence is saying is that big F and big G are the same except for the constant. And that's true of all antiderivatives of a function. They're the same except for the constant. Okay, 23 is another way of saying the same question. What's big F minus big H? Well, there's big F. What would happen if you subtracted big H? This would disappear. This would disappear. It would be negative 2 or 2. No, it'd be 2, wouldn't it? Because it was big F, take away big H. So if you take big F, take away big H, you're going to be taking away a negative 2. It's going to be positive 2. Okay? Then the other way around, then it would have been negative 2. Okay? But again, the emphasis there is the difference between those two is the constant. Okay? Now, where is big F increasing? Where is big F increasing? We didn't even graph big F. We just had an equation. We don't need it because this is little f. And what's little f compared to big F? Little f is the derivative, right? Big F is the antiderivative. So big F is increasing when little f is positive, just right from the chart. You don't have to even do anything with area there. Just, I mean, we've been doing it when we've been sliding and doing that stuff, but it's going to be from where to where? Negative 2/3 to infinity. Now I know, now that sometimes bothers people because you think of this 0 somehow has to come into play there. No. Where is big F increasing? Remember, big F, big G, and big H were just vertical shifts of one another. So where they're increasing from the same point. If we go back to this picture right here, okay, here's negative 2/3 right here. Look what happens when we move this left endpoint. Does that change where the parabola is increasing or decreasing? No, it's increasing from negative 2/3 to infinity. Over this way, and it's decreasing over this way. The left endpoint just is the vertical shift. That does not affect it. Okay, here's what it is. And again, some people are bothered by that. Yeah, it's easy to see that it's increasing this way. Yeah, because you're gaining area. But also, oops. Let's go back to that point. Let's go back right to here. Okay, let me say this one more time. What's happening to the area right through here? What's happening? But I'm losing negative area. When you lose negative area, that's a gain of area. So the area graph, big F, is increasing. And then once you get to here, you start gaining positive. So before you were losing negative, then after the 0, you're gaining positive. It's the same idea. Okay, so 25, where's big F decreasing? When little f is negative, which is negative infinity to negative 2/3, right? So these questions are very easy and quick to write down. Is big F concave up anywhere? Big F is concave up. Again, we're looking at big F, right? Big F is concave up when little f is increasing, which is the whole time. Little f is increasing here the whole time. Is big F concave down? No. That'd be when little f is decreasing. Little f here, the blue graph, is never decreasing. Again, just things from the chart. And then 28 is supposed to be this big, aha, exactly, which we've already done. Are F, G, and H all antiderivative? Yes, they are. So there's nothing really to justify, although how do you justify something's an antiderivative? Do the derivative of it. So to show that big F and G are antiderivatives, you do the derivative of them and show that you get 3x plus 2, but don't worry about that. So 28, the answer is just yes. So those are pretty fast. So 29, take you some time. Okay, draw those pictures. I want you to draw them. I want you to do the trapezoid triangle, whatever it is. Put the x over there. Work out those formulas. Show that it gives you the antiderivative. Last time you'll have to do that with pictures. Okay. One other part of the homework I want to mention is number 3 on page 320. And then I'm going to let you have the rest of the time to work. Number 3 on page 20 is one of your homework questions. They give you this little f graph, and they tell you that a of x is the integral from 0 to x of little f of t dt. Now they put this little f here. That just means the area under f. Don't worry about that little f. That doesn't mean anything. Just big A. It says, which is larger, a of 1 or a of 5? Now I want you, when you think about these, you don't have to write them both down as your justifications. You can just do one of them. But I think to really help you understand the concept, and I hope you've learned your lesson from earlier in the year, that that's important. To really understand the concept of what's happening here, I want you to think of these chart problems as slope and as area. And try to, now you should always get the same answer, no matter how you think about it, but I want you to think of both. So let's talk about slope first. That graph there is little f. Big A is what? Antiderivative. So that blue graph is really what of A? Slopes of A. So let's think of it in terms of slopes. So what's going to be bigger? A of 1 or A of 5? A of 5. Why?
Because it's increasing for longer.
What's increasing? You said it.
The A graph.
Why is the A graph increasing?
Because F is
Little f is positive, right? Since the blue graph is above the x-axis, it's positive. That means the slopes of A are positive. So that means A is increasing from 1 to 5. So that means the big A graph's going up. So A of 5 has to be bigger than A of 1. That's how we would have answered that earlier. Now, let's talk about in terms of area. What's A of 1 mean when it comes to area? Okay, this is the part that not everybody saw earlier, and I'm hoping you are now seeing. A of 1 means put a 1 into the A graph for x. That means right here, which means right there. A of 1 means the area from 0 to 1. Right? What's A of 5 mean? The area from 0 to 5. Look at that picture. What's bigger, the area from 0 to 1 or the area from 0 to 5? 0 to 5. Again, why? Because the graph's above the x-axis, so it's all positive area. So the area from 0 to 1 is this chunk. The area from 0 to 5 is this chunk. The area from 0 to 5 is bigger. So A of 5 is bigger. That's an area reason as opposed to the slope reason. They both give the same answer. I want you to be able to see both of them. On the quiz, I might ask you specifically for an area reason. Or if I don't say, you can give either reason. Okay? Or both. Cover your bases. Okay, so your assignment is at top line. If you want to start with 29 to get help on those graphs and stuff, that's fine. Otherwise, you can start with 2. And 3 through 8, 9 through 14 are both chart kind of things. So once you get through 29, the homework doesn't take very long at all. It's mostly chart, but it's mostly about making sure you understand kind of the big picture of what we're saying. All right, you can have the last half hour to work. I need to rest. There's an antiderivative.
Is it with integrals then?
Well, I mean that's an integral like this represents antiderivative. So
Yeah, it's gonna be a lot.